Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone and welcome back to Physics with Beth and Beth. I'm Beth and today we are doing some review for the long anticipated AP Physics 1 exam. In this video, we're going to be reviewing one of the 4 types of questions you can expect to see on the free response portion of the AP Physics 1 exam, which is the experimental design and analysis question. These types of questions try to test your ability to A, design an experiment to test a physics concept, B, analyze data, and C, recognize patterns from that data. So the best place to begin is the beginning, so let's dive right in. This is the little problem that we have, and this is actually a problem from a real AP Physics 1 exam that was given back in 2019. Fun fact, I took the AP Physics 1 exam in 2018, so I've been in the very shoes that you guys are sitting in. You stand in shoes, you sit on chairs. Hang in there, I've been where you guys are, it gets better, I promise. Okay, anyway, this is the problem that we have. We have a little spring-loaded launcher with a ball in it. We're able to put the ball in our launcher and compress the spring to 3 different locations, point C, point B, and point A. And the hypothesis that we're asked to test and then confirm or deny, or design an experiment that would test and then confirm or deny, is the value of K constant for the same spring? At first this sounds a little bit like a silly question. The question we're being asked is literally, is the spring constant for a spring? Which seems a bit silly at first, but actually it's a really good question because Hooke's law, where this little K guy is from, describes the behavior of an ideal spring, but we don't always know that our spring or spring-like thing behaves that way. Or even if it does, it might only behave that way within a certain range of stretchiness or compressiness. Maybe if we stretch our string too far, it gets all stretched out, like a slinky that you bent and no longer behaves that way. So this is actually a really great question to ask that real physicists or engineers might have to solve in a slightly more complicated but still very real context. So let's work on talking about how we would design a procedure to test this and exactly what we would do. The first part of this question that we're asked is to explain what physics principles we're going to be using to solve our problem. And so let's start by maybe thinking this through a little bit. We have this ball. We're going to put it in this launcher and compress our spring. Well, when we do that, we're going to be putting energy into it, right? And that energy is going to be stored as potential energy inside our spring. And then when we release our ball and it comes out of the launcher, it's now going to have kinetic energy, right? And those values should be the same because one of the fundamental laws of the universe is that energy is conserved, right? Well, that might be something that we're able to manipulate in order to answer our problem. So the physics principle that we're going to be using today is just the conservation of mechanical energy. Conservation of mechanical energy. And that answer is what this question is looking for. But you do need to elaborate a little bit. When I say the conservation of mechanical energy, I'm saying that will help us answer this question because the potential energy that is stored in our spring will be equal to the kinetic energy of our spring afterwards. But the kinetic energy of our ball afterwards. But how does that allow us to answer any questions about the value of the spring constant? Well, the spring constant is hidden inside the equation for the potential energy of the spring, right? Which is why this is a helpful fact. This is why we're able to use the conservation of mechanical energy in order to solve this problem. So you need to explain that. You need to say, not only are we using the conservation of mechanical energy, this is how this helps us find the spring constant because the potential energy of a spring is 1/2 K times delta x squared, and the kinetic energy, is equal to 1/2 mv squared. So if we take this and we rearrange that little equation for K, we can find K because it's going to be equal to mv squared divided by delta x squared. So this equation came from the conservation of energy, and that's how we're going to be able to calculate K. Well, there we go. That leads us right into the next part of our problem, which asks us what quantities we're going to measure and how we're going to measure them. And here we're being asked to list what the quantity is, the symbol and units of that quantity, and the equipment that we're going to be needing to measure that quantity. So we're actually on the little paper that you're given a little table and asked to fill it out. You won't always be, but in this question you are. So let's work on filling out that table. Well, here in part 1, we just came up with an expression that's perfect. It allows us to calculate K. So this is the thing that we're looking for. How are we going to go through the steps to measure these things in order to make this calculation? Well, the first quantity that we need to measure is this little m right here. So mass, which has a symbol of m and units of kilograms. And how should we measure the mass? Well, first of all, what is this mass of? Because we can say mass all day, but the mass of what? Well, we're talking about the kinetic energy of this ball after it's launched from the launcher, right? So the mass that we're talking about here isn't the mass of the spring or the launcher, but the mass of the ball. So this is the mass of the ball. And we could measure that with something like an electronic scale. Okay, if I know the mass, that's one of my 3 variables here. What's the next one? That would be this v, right? So this v represents the velocity of the ball after it's launched from the launcher, right? So there are a couple of different ways you can measure the velocity of the ball. You could do something really complicated with a photo gate that would also require you to measure the dimensions of the ball and then do all of that. Or you could just say, just get a motion detector. And a motion sensor just tells you exactly how fast the ball is moving when it leaves the launcher. Perfect, you're done. So our second quantity that we need to measure is the velocity of ball after launch. It has a symbol of v and units of meters per second. And we would measure that using a motion sensor. If we had to, we could do something complicated with like a meter stick and a stopwatch, but a motion sensor does all that math for us, and we're given a lab setup, so we can assume we have access to this kind of equipment. So that's all we have to write. We're going to use a motion sensor, and it'll give us the velocity. Now we have one other variable that we need to calculate, this little delta x squared. So this delta x, though, we have to remember what that represents. That delta x came from our expression for our spring potential energy, right? It's not talking about how far our ball travels horizontally while it's in the air, like from projectile motion. This delta x is from our equation for spring potential energy, which means it's talking about how far our spring is compressed. So I'm going to specify that this is the delta x of our spring, or stretch or compression of spring. I realize my handwriting is bad, but that's why I'm also talking. Stretch or compression of our spring that has a symbol of delta x. It has units of meters. And how are we going to measure that? Probably with a ruler or a meter stick, something like that. Don't overthink this too much. I am a chronic overthinker, and so I always struggle on exams. I tend to be the last person in a class to finish, no matter how good my grade is in the class. I might have an exam where I did great, I got one of the highest scores in the class, and I'm still one of the last people to finish, because I'm always overthinking things. Don't overthink on this part of the AP Physics exam. You can use a ruler to measure the distance, you're done. You can use a motion sensor to measure velocity, and that's it. You can use an electronic scale to measure the mass, and you're done there, okay? You don't need to go through some convoluted process in order to say, well, I can't directly measure the velocity, but this is how I could calculate it if I measured these other things. Then you end up going down this rabbit hole. You can assume you have access to some level of helpful equipment, so use those resources. So that is everything we need for part 2, or part B here. Whew, that was a lot. Okay, now I'm going to erase everything that I just wrote so that we can talk about step C, the procedure. Or actually, I'll leave these up here for now. So the procedure is, it can be tempting to write paragraphs and paragraphs whenever you get to the procedure section of one of these questions. If any of you guys had that problem that I did when I was like in middle school or junior high, where you're asked to write a paper teaching somebody how to make a peanut butter sandwich, and you have to like use the analogy of, or you have to tell the person to do every single step, like you have to tell your teacher to open the bag with the bread in it, then grab a piece of bread and then open the jar of peanut butter and grab a knife and put peanut butter on the knife, then use that knife to spread the peanut butter on the bread. You don't have to do that. You can assume that the person performing your experiment is a scientist with at least some basic level of common sense. So you don't need to explain, you put the ball on the scale, then you turn the scale on. Actually, no, you turn the scale on first, then you zero the scale, then you weigh the scale, the ball on the scale, and then you read the measurement and record it. You can just say, weigh the ball using the scale. That's okay, you can do that. So that would be your first step of the procedure. Measure the mass of your ball using the electronic scale. That's all you need to say. You don't need to walk somebody through the steps of how to turn the scale on or being careful to zero it or anything like that. You can assume that your person who's performing this, who's following your instructions, knows how to use the scale. Thank goodness. You've only got 25 minutes on average for this question, so don't spend time explaining things that you don't need to. All right, so if our step one is to tell our person to measure the mass of our ball using the scale, well then, what's the next thing that we're going to have to do to measure this? Well, we're going to need to take a measurement of our kinetic energy and compare that to our potential energy and make sure that this potential energy actually calculates our potential energy, right? In other words, we're trying to prove that this value is constant no matter how much we stretch or compress our spring. So we should calculate it at 3 different points and see if it truly is the same. So what we should do is compress our spring back to, say, point A, launch our ball and measure its velocity. Also measure how much our spring is compressed to point A. So that would be step 2 of our procedure, is to input our ball into the launcher, compress it to point A, launch our ball, and measure the speed of the launch, or velocity rather. That's it. We don't have to tell somebody how to use our motion sensor or something like that. We can just say, use the motion sensor to obtain a measurement of velocity. Also, be careful to notate that you need to record these things. So not only do we take a measurement of our velocity, we then record it. So you should write something along the lines of, use the motion sensor to obtain a measurement of velocity after the ball's launch and record. That's important. They're going to be looking for that, and if you don't include those 2 words and record, you might be docked points. Another thing that you really want to remember to do is to remember to include multiple trials of this experiment. So when I'm compressing my spring to point A, I might want to say not only to do that once, but to repeat 3 times and then take the average of my 3 measurements. The AP board really loves you to say that you're going to repeat an experimental trial 3 to 5 times. Those are sort of their favorite numbers. Miss Beth and I like the number 3 because it's a pretty number. It's a nice number. It's easy to remember. But whenever you perform an experiment, make sure that you tell them to do that experimental trial 3 to 5 times, or else you'll be docked points, because one measurement isn't always going to be accurate, right? You should take an average of multiple measurements to reduce that experimental uncertainty. All right, so that is our step 2. Compress our spring back to point A, measure that distance, launch our ball, use the motion sensor to measure the velocity and record our velocity, then repeat that measurement 2 more times for a total of 3. Then we need to do the same thing at points B and C. You can just say, repeat step 2 for points B and C. You don't need to write out all of that again. You can assume that the person doing your experiment has some level of common sense, that if step 2 applied to point A and you say do that, but do point B instead, they'll understand. So that can be your next step. And record the velocities, of course. And that's all that you need to say. So, in summary, step 1 we said was to measure the mass of our ball using an electronic scale. Step 2 was to compress our launcher to point A and record that distance, then launch our ball and measure its velocity with the motion sensor, then record that. And then repeat that trial 2 more times for a total of 3 experimental trials. Our next step was to repeat that previous step for points B and C. And now we have all of the data that we need, and we're able to move on to step D, which is graphing. So now I am going to have to erase this. So figuring out how to graph data is a really important skill that can be pretty challenging sometimes. In fact, of the 4 questions on the AP Physics 1 exam free response section, 2 of the 4 questions involve graphing to some large extent as part of the problem. So being able to visualize data and graph it and then derive conclusions from that graph is a really important skill that's very heavily tested on the AP Physics 1 exam. So for this graph, we want to think about how we could graph all of our data, which was our velocity. So the 3 quantities we measured were mass, velocity, and also delta x. And we want to figure out how we could graph these quantities so that we can find k from that graph. We can find our spring constant from that graph. Well, whenever you're trying to do something like this, think about slope. We calculate slope from being rise over run, right? And by that I mean rise is how much we go up and down on the y-axis, and run is how much we go side to side on the x-axis, right? So anytime you're trying to figure out how you might be able to obtain a measurement like this from a graph, think about rise over run. If you have an equation and you have something in the numerator, that probably means it should be included in your rise in some way. And if you have something in the denominator, that means it should be included in your run. Or in other words, if it's on top, it should be on your y-axis. If it's on bottom, it should probably be in your x-axis. Now there's some variation to that. You want to think about which quantities you can measure, which ones you're varying over time, and things like that. But rise over run can really steer you in a really good direction on a lot of these problems. So if we have k is equal to mv squared over delta x squared, maybe the way that we should calculate this, well, I've got v squared on top and I have x squared on bottom. Maybe I should use v squared for my y and delta x squared for my x. Well, that wasn't so bad. Now, the one question you might be thinking is, well, but m was also something I had to measure. Why don't I include that on my y-axis? Well, m wasn't something we changed though, right? We measured that, we had one measurement for it, and then our mass of our ball didn't change at all. We didn't do different trials with different balls of different masses and then take different measurements. We just measured it once and now it's a quantity that we know. So I don't think that's something we should put on the axis because, well, we want our thing on the y-axis to be something with multiple values, right? Something that changes. Same case with the x-axis. So that's why I said I think I want v squared to be my rise and delta x squared to be my run. So if I graph this, and here I turn my notes over, on my y-axis, I'm going to put v squared, which has units of meters per second squared. Remember your units, this is physics, so units matter, they're super important. And then on my x-axis, I'm going to put delta x squared, which has units of meters squared. Now, you're also asked, as part of this problem, not only to define your axes, but also to say what you would expect the data to look like. So we might see something like this. Well, I know if my delta x is low, that's like when I'm compressing it to point C here, for example. So my delta x is low, I'll say this is like point C. Well, that's not a lot of potential energy, so my kinetic energy is going to be low as well. So I'm going to probably have a lower velocity there. We don't need to calculate what it would be. In fact, you don't have enough information to calculate what that velocity would be. But you could expect lower delta x, lower v. Then when we measured point B, whenever we compressed our launcher to here and then measured its velocity, well, it's being pushed back a little farther. It should probably be launched a little faster from the spring, right? So maybe something like this. Okay? And then here's point A, where we're compressing it the most. So whenever we're compressing it the most, it should be launched the fastest from our little launcher, so we might expect to see something like this. And then I'm going to do one thing that's really important on the AP Physics 1 exam. I'm going to draw a little line through these points, a line of best fit. That's really important. Don't forget it. The AP Physics 1 exam people are very nitpicky about lines of best fit. They want to see not only that you can predict what your data might look like, but then recognize a pattern that is occurring between those data points. So if I can recognize the pattern, I need to draw that pattern, in this case, which is a line. So line of best fit, don't forget it, it's important. So I think that is everything for part D. We have our graph, we have our axes defined, we drew what our data would look like, and we drew a line of best fit through it. That's part D. Now for part E, we have to say how we would calculate our value of K from that graph. Well, there are a couple of different ways we could do that. Well, we just said our slope is rise over run. Our rise is v squared, our run is x squared. So if we do K, that would just be equal to our slope. Well, but not quite, right? Because here we have v squared and here we have x squared. There's one other little variable included in our calculation for K, right? That's this m right here. So our value for K from this would be slope times our mass. So that's what we would do to calculate K from our graph. We would take the slope of our graph and multiply that by mass. And how would we tell if K is constant? How would we use our graph to really answer this question? Is our spring constant constant for our spring? We could use that by calculating K for each of these points here. Our v squared divided by our delta x squared, then multiplying that by m. And if it's the same, then it's constant. Another way you could tell is if you have a line with a constant slope that is a straight line going through all three of those points, then you also know that K is constant. So that's two ways we could use our graph to confirm or refute our little statement here. Whew. Okay, that was a doozy. Thank you so much for sticking with me through all of that. It felt like a lot. I know this was a long video for us, but just break it down step by step and it's not that bad. If you guys have any questions, please let us know in the comments and we'll do everything we can to get back to you. But thank you so much for watching this. I hope you guys have a lovely day and happy physicsing.